My name is Doug Ackermann. I'm from SEGGER and I'm marketing manager there. I'm going to introduce our ecosystem that we can provide for RISC-V-based embedded systems. So just to give you a tech, when your prime concern is performance or space, and we have the tools to get you there, and I will show you in a sample how dedicated we are to provide just that. So let me start with a quick introduction of the company. So we're a company which has been introduced in 1992. So we are operating for more than 28 years. Our headquarters is in Monheim in Western Germany. We have offices in Boston, Massachusetts, and Silicon Valley, and a fairly new office in Shanghai, in China. And to serve our worldwide customers, we also have a worldwide distribution network with more than 30 distributors. The company itself has 60 employees, with managing director Ivo Gallenbrügge and CTO Alex Grüner. Our founder, Rolf Segger, is still very, very active in the company. Actually, he's basically still running the technical development and a lot of other things. So that's a very good setup because we're still owned by the founder, and he's very active in there, and he's still running the company. Okay, so this is one thing. Let's next get into the products. So we have basically 4 product groups depicted by these icons here. So the black ones to the left are the hardware products, debug probes with the jailing that many people actually know. Then we have software tools on the PC side, so which run on Linux, Mac, and Windows. So then we have the embedded software. That's actually the part of the products which we started with. So we started with Nartos, and over time we added a couple of other things like stacks for communication, like IP, USB, and graphics user interfaces, bootloader for firmware updates, security libraries, and so on. And then the 4th group to the right, the blue box, is the production programmer. So we use the same Flash programming algorithms that we use with jailing also in production, and they are basically the fastest in the industry and go really close to the absolute maximum speed that is possible with the target hardware. So that's for a quick overview. So typical embedded system. You have a microcontroller where you have running the RTOS, can add a lot of software libraries, and we provide all these tools so that you can focus on your application. So that's the main message here. Every bunch of libraries and proven libraries. And I'll tell you now why they are proven from one perspective, because one perspective within our company is that we are user and developer at the same time. So we use our software tools actually to develop our embedded software, to develop the firmware of the jailing debug tools, and to develop the firmware of the Flash programming tools. And we use the jailings to debug the software running on some targets, debug our flashes, debug the jailings themselves, and so on. So our embedded software runs inside the jailing, runs inside the flasher. So as you can see, always we have this connection being the application developer and the application user at the same time. And this actually was the quality that we expect from our tools that we are using. We basically are forced to make our own tools better that we offer to the market. That results in high reliability. We have the features of the tools are very close to what you actually need in your development process. We rarely try to go to the mainstream and hit the next buzzword in our development. So that's what you can expect from SEGGER here. So this is the same sample, just with some hardware shown. So we have on the left side the debug tools, on the right side some target hardware running our RTOS and so on. So just a quick overview over some products, and I will give you a short example of what I've been talking about: getting performance high, getting resource usage low. So J-Link is a family of debug probes. Meanwhile, we have a bunch of products that can be connected with Ethernet, can be connected via Wi-Fi, which is interesting if you have moving devices or devices with big moving parts like robots or moving robots, stuff like that. We have compact versions of these. So meanwhile, it's a grown family, and that's actually more than 600,000 devices out there in the market. So basically, we think that every developer out there probably has a J-Link on his desk, and the J-Links also support the RISC-Vs. So this is the J-Link Wi-Fi that I mentioned. Let's skip over it because I've a bit more slides than I actually need. So next group are the software tools. The biggest ones here is Ozone. This is actually the debugger for the J-Link family. System View is an event tracker or event monitoring system where you can actually see which tasks are executing, which interrupts are firing, and so on. So you can find actually misbehavior that you cannot spot with the debugger. So it's a different view on your system. You can use it for system verification and so on. And then to the left, we have the icon for Embedded Studio, which is our IDE. And this IDE includes its own compiler, its own linker, and we've run this actually through a readers test last year. So at the end of last year, which with the result being provided actually just before Embedded World. So there have been 10 readers trying out our product and giving rates for usability, for performance, and so on. And we managed to get the highest rating that has been achieved so far with the electronic readers test. So that's what you can see with the 4.5 stars. We're very proud of it because that's our goal, being having high usability and providing tools that enable you to get to high performance products and so on. So now I promise you that I go into a bit of detail, not just listing our products. So let's look at our linker. That's just one of the many pieces we use. We have the compiler that's based on the LLVM. We have added some more things to it, so we can actually reduce the code size and still keep up with performance. And have added some tricks in there. And then we have our own runtime lib, our own floating point lib, which consists of a lot of assembly code in many places to optimize size and actually make it easy to optimize by the linker. And I'll come to that in a moment. So when I talk about the linker is a difficult product because that's something when you develop, you create your C code, then you run it through the compiler, it's translated into machine code. And when you have the machine code, you need to link all the different pieces of machine code the compiler has created from your C files. And then when you have all that, that one goes to the target system. And the linker is actually a very good spot where you can do a lot of optimizations after the compiler has been run. And to explain it a little bit more easy, I'm going to use some analogies. So when we're talking about programming, we have the code. When we're talking about writing, we have a book. When we talk about programming, we have a library of functions that's similar to a dictionary in writing. When we talk about a function, we can talk about an idiom, for example. And when we talk about size optimization in a book, you would remove a page, for example, so you have less pages. And when we talk about execution speed, it, for example, could envision the browsing of pages through a book. So that's just trying to make it a bit more clear what's going to happen behind the scenes. So now let's go into the details. So there's a method that is called relocation. What we basically do is when we write a book and we have written a story, we can write a certain piece of information into a paragraph, and then we can afterwards think about, okay, it would have been better in a different place. So we take that paragraph from that page and put it to another page. And the reason why we want to do that is because depending on where code sits, we can save on jump instructions. So a jump instruction basically lets you jump to a different place in the code. It would basically be like moving over a couple of pages. And the more pages you have to browse, the longer it takes, and the more space your book basically has, because you always need some markers which say, okay, jump here, jump there, jump back, and so on. So when we can reorder the code, we can actually get rid of jump functions. And there's one thing more, and that's depicted with the areas, the white areas on the lower side of the slide. To the left, you have 46 blocks, which are basically 46 bits or 8 byte. This is actually a long-range jump, and you have to jump over long distances in RISC-V. You need actually 2 instructions. And as they are in the RV32EI and as the SR32-bit functions or commands, you have 64-bit. You have a little bit lower range between the addresses you want to jump to. You can actually reduce that to a single operation. That's just a JAL. And if you even have smaller area where you want to jump, you can actually use a compact instruction set that has only 16-bit. So you can see there's some potential, and even in some cases, if the function is called a single time, then you can basically reduce the hit of the jump to 0 by placing the code actually directly into the program flow. So that's what's depicted here. Well, let's get on to the next one. Link time optimization has a lot of different options that you can use. For example, you can remove unused code. So basically in a book, you would look for empty pages or pages that are actually not read because there's something on there that nobody is interested in. The linker does something similar. It goes through the code it has and basically does some sort of code coverage analysis and sees where there are sequences that are actually never hit. And if they are never hit, it will take them out, reducing the code, tearing out pages. Then when you write a book with lengthy explanations and you repeat those explanations all over again and again and again, it will disturb your reading flow. So you usually, at some point, you will replace such lengthy explanations with idioms or something else. And on the linker side, something similar happens. If the code includes sequences that are run over again and again and again, then the linker will basically replace these structures, put in a branch function, and go to a different spot where it has stored this exact code, and then return back. Okay. So that are the methods before, they have been locally applied, and that's also what the linker can do, is basically do it globally, so across multiple volumes, if we are talking about a book. So in terms of the linker has different object files and can look at these. And usually the linker just looks at one object file at a time, and then it's done with its work. The SEGGER linker actually uses relaxation. That's how it's called, which means that it can actually take code from one object code file and place it next to something which is unrelated to the original object file. And by rearranging this, can optimize the execution order, so it can optimize the jump instructions. It can actually use the same function optimization that I've outlined before, so it can replace the code sequences and so on. And this is usually done on sort of on the code on a certain code level, which is basically which is based on source code in a way, in the ELF information. And the next step further is actually outlining. So you go one step deeper, and this step actually allows you to optimize third-party libraries, because now the linker goes into the binary code of these libraries and looks whether there are similar functions, whether there are unused functions and stuff like that. By doing that, it can even compress code even further. With all these methods we have outlined here, so from the compiler to the libraries and all the methods we're using inside the linker, we can actually reduce the size of a real-world application by 75%. So keep that in mind when you have space-constrained systems. This is a good method to do that. Okay, so basically, as I said, I'll try to introduce our company. I have just a little time left. So let me get quickly over the remaining products. System view I've explained before. You're looking at different tasks and how they interact with each other. Then we have our software libraries. These include our security libraries, which is encryption, authentication, and so on, communication libraries, user interface, and so on. So you see RTOS, just a quick word, it's safety certified by 61508 or 62304. It can also be used in 26262 applications. And one important thing to note is when we certified it, we basically used the code we already created. We did not adapt the code and received the certification with the original code. And let's talk with connectivity I've mentioned before, so USB, IP, and so on. Security, we can support basically a lot of things like key provisioning, encryption, authentication, and so on. And yeah, let's make all that. And yeah, I'll finally just introduce mcompress Go to you, because that's very interesting. Usually you need lots of RAM for compression on the target system. The algorithm used here does not need as much RAM. It needs nearly 0 RAM. So if you have communications where this is a good, where you need to compress data on your system, this is one thing to go. Okay, I'll skip over the rest because my time is running up. Thank you for listening and enjoy the remainder of the show. I'll make myself available for video calls within the next hour. So if you have any questions that you want to have in person, then just contact me on our presentation here at Embedded World.